Welcome to the 7th video of the physics lecture series for the National Science and Mathematics Olympiad. In this video, we will discuss Archimedes' principle. You might recall the story of Archimedes with the golden crown in the bath from our lecture on fluids. Archimedes discovered at that moment that he could calculate the volume of the crown by the amount of water displaced. Dividing the mass of the crown by its volume gives its density. If it is the same as that of gold, then the craftsman was honest. If it were closer to that of silver, though, that proves that the craftsman replaced some of the gold with silver. It is a great idea to measure volume with the amount of water displaced. But Archimedes also noticed another thing that you might have noticed as well, that fluids push up on objects, making them feel lighter. For example, it is much easier to lift a rock in the water than on the shore. How can we make sense of it, and how does it relate to the amount of water displaced? Take a look at the experiment presented here. There is a beaker filled with water and there is a little hole in it. So if the water level rises, the excess water will drip down into the container. We measure the mass of a weight and find that it is 5 kilograms. According to Newton's second law, F equals m times g. This means a weight of around 50 newtons. Then we submerge this weight in the water and see that the weight is reduced to 30 newtons, so we will measure a mass of only 3 kilograms. Then we measure the weight of the displaced water, and we will find that it's around 20 newtons, so its mass will be around 2 kilograms. From this experiment, we can conclude that the submerged objects weigh less exactly by the weight of the water flown out. This is Archimedes' principle. But why does the submerged object weigh less? The physical reason behind it is the buoyant force. This is the force that acts on any object submerged in a fluid, and its magnitude is equal to the weight of the displaced fluid. By denoting the weight with W, we can use the following formula to calculate the buoyant force. Fb equals W minus W apparent. So the buoyant force equals to the weight of the object minus its apparent weight when it's submerged in the fluid. This principle is true not just for objects completely underwater, but also for those that are partially in the water, just like this ball. In general, we could say that any object, totally or partially immersed in a fluid, is buoyed up by a force equal to the weight of the fluid displaced by the object. We can calculate this force by multiplying the density of the fluid by the volume displaced, which is the volume of the object if it is entirely underwater, and by the gravitational acceleration, g. This principle also helps us understand how boats can float. If the buoyant force is equal to the weight, the object floats, otherwise it sinks. In general, any floating object displaces its own weight of fluid. An interesting example of this is airships or dirigibles, which contain gases less dense than the surrounding air. This is the same principle as with balloons filled with helium, which can rise up in the air because the buoyant force is larger than their weight. Now, let's get back to the story of Archimedes again. He didn't use Archimedes' principle to solve the problem. He only measured the volume by the amount of water displaced. But you could actually use the principle to solve the problem, using the crown and a piece of gold with equal weight. Think about it. How could you do this? Finally, I brought you an interesting example. You are also submerged in a fluid right now, in the air. So the buoyant force acts on you as well, just like on airships or balloons. Let's calculate how much lighter a person is due to this force. First, we have to calculate the volume of a person. Let's assume a mass of 70 kilograms and a density close to that of water. Dividing the two, we get a volume of around 0.07 cubic meters. Then we can get the buoyant force by multiplying this volume with the density of the air and the gravitational acceleration. Substituting the values, we get a buoyant force of around 0.84 newtons. A person's weight is this much smaller due to the surrounding air. Translating this to mass, this means around 0.08 kilograms. So this is not a very large effect. Thank you for your attention and see you in the next video.